So one big issue with coaxial cables, and again I'll use my visual here, is how do you connect the end of the cable to some useful microwave or radio frequency device. So every coaxial cable you see will have some sort of connector at the end of it. And this allows us to connect it to some device that has been designed to accept that connector. Now, there are many microwave connectors out there, and so the question is why, and what are the benefits of each of them. Generally speaking, we find that different coaxial connectors will work to some different upper end frequency. They have different bandwidths. Generally speaking, as you make the connector more sophisticated, higher manufacturing tolerances, oftentimes better materials, conducting materials in there, the cost will go up, but also the performance will go up. And by performance, we mean at what frequency can we use it? What's the upper end in terms of the connectors? This shows a nice chart here of the different connectors and then the sort of the upper frequency for a number of microwave connectors. And you can kind of see them to show that there are many of them. And this is by no means exhaustive. There are many different kinds of microwave connectors that have been designed and are manufactured. One word of warning on these upper ends, the bandwidth there. For example, if you look at BNC, it goes up to about 4 gigahertz. This is subjective, I guess, in terms of, that the upper end. As the frequency goes up, basically the performance then will begin to degrade. And by performance, electromagnetically, they'll be clear that there's a discontinuity in the transmission line where the connector occurs as you go up in frequency. But it's not like it's a step function in frequency. This plot here, or this chart that shows 4 gigahertz for the upper end, it's not like if you use a BNC that it will work wonderfully at 3.9, but if you go to 4.1 gigahertz, then it won't work at all. Again, there's kind of a gradual degradation. So where you define the cutoff frequency is sort of depending on your purposes and what you're trying to achieve. But this does give you some idea of the performance as a function of frequency for these different connectors. Now I'm going to pick a few of these connectors and talk about them and give you some idea of their performance, their costs, and why or why not we may use them in our system. So the first connector I'm going to talk about is the SMA connector. And it really is the workhorse microwave connector. If you go around and look at the most popular microwave connector, I would imagine that you would find it would be the SMA. So this shows the connector at the end of a coaxial line, and this shows a device, a component, a 3-port device in this case, that is built to be attached via the SMA coaxial connector. And you see these connectors here, and you can see that they mate with the connector for the SMA. One of the great things about the SMA is it works up to fairly high frequencies, certainly into the gigahertz or tens of gigahertz, let's say up to about 20 gigahertz. And again, this is rough. It's not like it just falls off the table at 20 gigahertz or anything. By microwave standards, it's relatively moderately priced. I would say probably the only drawback from SMA is SMA. If you look at it, the diameters here are about, they're less than a centimeter. And so that limits the size of the coaxial cable. And so if you have a very high power application, you certainly would not be able to use SMA connectors. So on transmitters, you may not see them as much, but certainly on receivers, when you're up into the gigahertz and you have a connectorized design, where devices are connected with coaxial transmission lines, you'll find that SMAs are quite prevalent. Perhaps the second most prevalent coaxial connector that you find is the BNC connector. And it fits about in the same size coax as the SMA. So again, it's low power connector. The benefit of the BNC is it's easy to connect. The SMA had threads on there, and you literally have to turn it. You could use a SMA wrench to actually connect it to the devices, although be careful and don't over torque, or otherwise you'll destroy the connector. BNC, on the other hand, is just push and turn. If you're probably familiar with the BNC connector in labs, a lot of equipment has BNC connections, so you just push and turn and it connects, and it's easy to get coax on and off. One thing about BNC is it's a lower frequency, lower bandwidth. So you see BNC connectors on test equipment, for example, that is more in the what we call the video or RF region below perhaps 2 gigahertz. For example, in this test equipment, notice it's a source and it's generating a signal at 50 megahertz, which is still high frequency, but of course it's not 5 gigahertz by any means, where you might use an SMA. So, generally speaking, don't push this connector past 3 or 4 gigahertz. The most likely coaxial connector that you've probably encountered is the F connector. And the F connector is a connector that's used on coaxial lines associated with consumer products like TVs. Again, that's less prevalent now that we've everything switched to HDMI, but certainly back in the day of VCRs, for example, and these connectors were prevalent. And this is the connector on my coaxial for the visual there. If you look at it, see if you can see there if it shows up or not. You look inside. And I kind of hesitate to call this connector. I mean, it does connect to the device, but the center conductor of the connector itself is simply the center conductor of the coax that's been extended through and cut. So really the F connector has an outer conductor that's used for connecting to devices. It's, again, kind of a screw on. It's threaded. But the inner conductor is just whatever the inner conductor of that coax cable happens to be. You cut it off there, and oftentimes that gets kind of ragged and cut, and it's not very uniform. The length of it is not very uniform. And so the F connector is not really a very good connector at all. And it's not particularly reliable. It can be difficult to connect. So why did it's so prevalent? Well, for one reason and one reason only, it's cheap. And so, like most consumer products, cost is the overriding factor. It doesn't work very well, but it works well enough, and it doesn't cost much. So people used it for years and years, several decades. The N connector, shown here, was really one of the original microwave connectors. For connecting, we started making microwave components that are connected with coaxial transmission lines. Again, N connector was sort of one of the originals back in the 40s and 50s, let's say. It was eventually replaced with the SMA. The SMA became the preferred, but for a couple of decades after World War II, the N connector was the most prevalent. One thing about the N connector that's still useful is it's larger, and of course that's one reason people went to SMA, because it had less bulk than the N connector. But you can connect a larger coax diameter to the N connector, and so if you have a high power application or a higher power application than what SMA would be useful for, you could use this N connector. And for the most part, I would say these days, if you do see a N connector, it's going to be on a larger coaxial cable, which means that it's for a application where the power is higher, or simply you're trying to minimize the loss in a very long cable. Bandwidth-wise, it doesn't go quite as high, probably, as an SMA. And again, I always want to tell you to look at these numbers with a bit of a grain of salt. These are very subjective numbers. Again, it's not like there's a sudden degradation in performance. Just in general, as you go up in frequency, things will get worse. So the UHF connector, shown here, is sort of a cheap version of the N connector, and so it was used for a while in a lot of consumer products. These days you probably want to see it in consumer products where, again, the power handling capability needs to be a little bit larger, and so you have to use a bigger coax, but that is relatively infrequent. But I add this in here sort of for completeness. Another connector you may be familiar with is the what's called the RCA connector, and the back of stereo equipment. Oftentimes there'll be plugs like this, and you take coax and insert them into these plugs to connect up audio and video ports. So these are used in a lot of consumer products. Again, they're coaxial connectors, but they really are not RF connectors. These are used primarily for audio and video signals, and so it's really signals that have bandwidth that's less than 50 megahertz. The benefit of this is they're cheap and easy connect. You just push them in and pull them out. There's no turning. There's no connection really there. And the reason you get away with that is, of course, that the signals are at much lower frequencies, generally speaking, for audio or video. The last connectors we're going to talk about are APC connectors, APC 7 and APC 3.5, and 7 is in millimeters, which is the diameter or the outer conductor of an APC 7. It really is the top of the line connector rather, in terms of performance. You see these type of connectors on high-end test equipment, usually like network microwave analyzers. They got the best performance, but they cost the most dollars. If you go to most microwave labs around the world, and certainly microwave labs in academic institutions, and you find one of these connectors on a network analyzer, and you look at them, and the actual inner and outer conductor, the gold material right here. If you look at those, they're kind of ruined. They're scratched up. They're messed up. We spend all the money to make the performance really good, and then when you bring in the lab, engineers, when they connect them incorrectly, and they're more or less destroyed within within a few days of arrival. And I don't mean destroyed in that they no longer work at all, but certainly the performance that you put all the money into is greatly degraded. So I just point that out because if you're using an APC 7 connector, if you're using a network analyzer, make sure you know how to connect these darn things. Again, there's sort of have some knowledge involved in terms of how to connect them and connect them well, so you don't harm them. And so don't try to wing it. Make sure you ask somebody that can tell you. I'm sure there's something on YouTube or something that will tell you how to connect an APC 7 connector. There seems to be something on YouTube to tell you how to do anything and everything that you're interested in. There's another version called APC 3.5, and in that case the outer diameter is 3.5 millimeters, which is pretty darn small. Now, why would you use that? That is for very high frequency applications, going up to, let's say, 40 gigahertz or more. And the reason it has to be small is so it doesn't generate those waveguide modes. Remember, we said there's an upper end on how big a coax can be, and that upper end is based on waveguide modes. But those waveguide modes will be generated as you first when you go up in frequency. So if you go up in very high frequency, you need to then make the coax smaller to try to eliminate those waveguide modes, which is why there is something called APC 3.5. Again, if you're using that, almost certainly you're talking about signals that are in tens of gigahertz upwards to 40 gigahertz or so.